Okay, gang, this is where we left off. We were working on derivatives and integrals of exponentials. So we did a couple problems like this before you left. We probably need a little bit more review. So just remember up here, our general rule, if we're taking a derivative of an exponential, okay, it's going to be that exponential times the natural log of the base. Remember, the base is a constant, okay, times the derivative of the exponent. And remember, the exponent obviously is some sort of expression involving x. So starting with this first one right here, let's get this guy set up. Okay, so we have to do the derivative, okay, of y equals 6 to the power of 5 minus x minus 7 to the power, 7 times 5 to the power of 4x. Okay, so we're going to have to take each of these terms one at a time. Okay, so this guy is just real straightforward. Okay, your a is 6. Okay, that's your base. And then your u, okay, is your 5 minus x. So just applying the rule, okay, we get dy dx equals a to the uth, so it would be this expression, 6 to the power of 5 minus x, times the natural log of a, which obviously is 6, natural log of 6, times the derivative of the exponent, the derivative of u, 5 minus x, so that derivative would be negative 1. Bring your minus sign down. Okay, now right here we have a constant multiplier of 7, so that guy just stays out front. And then I take the derivative of 5 to the 4x power. So again, your a right here is your 5, and your u, okay, is your 4x. Okay, so we go a to the uth, okay, so 5 to the 4x power, times the natural log of a, so it'd be the natural log of 5, times the derivative of u, okay, which would be 4x, so we take the derivative and we get 4. And then from here on out, we're just cleaning things up. Okay, not much you can really do here other than just put the coefficient of negative 1 out front. So we have the opposite of 6 to the 5 minus x power times the natural log of 6 minus, okay, now right here I have a constant multiplier of 7 and a constant multiplier of 4, so I can multiply those together. Okay, so that's going to give me 28 times 5 to the 4x power times the natural log of 5. And there's not a lot else we can do with that guy, so that would be it. Okay, let's see the next one. Okay, we are taking the derivative, of y equals the third root of 10 to the x minus third power. Okay, so the first thing I would do is get it into a form where you can actually work with, and that cubed root obviously is not what I want to be working with. Okay, so we're going to get it out of root form. This would be the same as 10 to the x minus third power, all to the 1/3 power. I would use your power of a power rule all the way back from Algebra 1, so just multiply these two exponents. Okay, so this would be the same as 10 to the 1/3 x minus 1 power. Okay, and now we can use our general rule where you let your 10 be your a, okay, and your u is your 1/3 x minus 1. Okay, so now we do dy dx equals, okay, going back to your same general rule right up here, okay, we're going to go a to the uth, Okay, so 10 to the 1/3 x minus 1 times the natural log of a, and a is 10, times the natural log of 10, okay, times the derivative of u. And u is up here, and we take the derivative of 1/3 x is just 1/3, and the derivative of -1 is 0, so we get 1/3. Okay, now we just look, is there any way we can clean this up? I would say about the only thing we can do is just put the 1/3 out front. So this guy's going to come out front. Okay, we could go back to exponential form. I'm sorry, we could go back to root form here if we wanted to. Okay, because don't forget that guy right there is the same as this guy. But you could leave it that way as well. It doesn't really make any difference. I'm going to go back to root form because I'd rather be in root form. Okay, so I get 1/3 natural log of 10, okay, times the cubed root of 10 to the x minus 3rd power. And I would say that that's a good form here. Okay, we could leave it that way if you wanted to. Okay, or notice we could go back to our properties with logarithms. I could take this coefficient and put it back, okay, in exponential place. Okay, so this would be the same as the natural log of 10 to the 1/3 power, which is just the cubed root of 10, okay, times the cubed root of 10 to the x minus 3rd power. Okay, so that's another acceptable form. Either one of those is in good shape. It's just a matter of which one you want to use. Okay, on to the third one. Okay, so we have to do dy dx of 4 times the sine of 8 to the 5x power. Okay, so this one's a little bit different because we have a trigonometric function there. Okay, again, the 4 out front is just a constant multiplier, so this is just applying the chain rule. Okay, if we let our first iteration of u be this entire thing, this would be like taking the derivative of 4 times the sine of u. Okay, so we get dy dx equals 4, which is my constant multiplier. Then if I take the derivative of the sine of u, I get cosine u. So cosine of 8 to the 5x power times the derivative of u. Okay, so that would be times dy dx, okay, of this 8 to the 5x power. Okay, so this is where I have to go back again to my general rule, derivative, okay, of an exponential. Okay, so let's see what we got going on here. So I have 4 cosine of 8 to the 5x power, okay, times the derivative of 8 to the 5x power. So it's going to be a to the uth, again, letting the 8 be your a and your 5x be your u. So I get a to the uth times the derivative of a, which would be times the derivative of a times the natural log of a. So that'd be the natural log of 8, okay, times the derivative of u. Okay, so when I take the derivative of 5x, I just get 5. Okay, so from here on out, we're just cleaning things up. Okay, so let's see. I've got a constant multiplier here and a constant multiplier here, so I can multiply those, so that's my 20. Okay, I have an 8 to the 5x power. I have a natural log of 8. And I have this cosine of 8 to the 5x power. And I don't see anything else you can do, unless, of course, you wanted to mix and match the order that you write those 3 portions of your answer in. Other than that, that's about all you can do with it. Okay, so those are the easy ones. We get here to the tougher ones, and these are the ones that normally give students some problems, and I certainly understand why. remember, we cannot use this basic rule right off the get-go. Okay, the reason being is that this exponential and this exponential have a difference. Okay, in this exponential, a is a constant. Okay, and your u is your algebraic expression. Okay, but over here, notice that we have an algebraic expression for our a and an algebraic expression for our u. Okay, so that poses a problem, and what we have to do is we have to pull these two things, these two expressions away from each other. We have to get the a and the u away from one another before we can take the derivative. So this is where we use exponential, let's see, what are we gonna do here? Logarithmic exponentiation. Okay, so the very first thing I will do is take the original function and take the natural log of both sides. And of course, you can use a different log if you want to. So I'm not even gonna deal with the derivative until I get this expression in a form I can work with. So taking this original function and take the natural log of both sides. So we have the natural log of y equals the natural log of x plus 1 to the x plus 1 power. And on the right-hand side, what I can do is use our rules for logarithms. Okay, and we can use our power rule, and now I can take this exponent and move it out front as a coefficient. Okay, so we get the natural log of y equals x plus 1 coming out front times the natural log of x plus 1. Okay, and now we've got this base and this exponent pulled away from each other. So now I can differentiate straight across and we'll be in good shape. Okay, so now that I take my dy dx, okay, differentiating the left-hand side, well, the derivative of the natural log of y is 1 over y times the derivative of y, which is dy dx. And obviously, that's what we're looking for. On the left-hand side, you have to use the product rule, okay? Here's your first function, here's your second function. So we go the first times the derivative of the second. So we would have x plus 1 times the derivative of the natural log of x plus 1 would be 1 over x plus 1 times the derivative of x plus 1, which is just 1. Okay, plus, let's see, the second times the derivative of the first. So it'd be natural log of x plus 1 times the derivative of x plus 1, which is just 1. Okay, so let's make sure we got this right. We got the first times the derivative of the second, so it'd be x plus 1 times 1 over x plus 1 times the derivative of x plus 1, which is 1, plus the second times the derivative of the first. Yeah, we're in good shape. Okay, so let's clean up the right-hand side. So we have 1 over y equals, 1 over y times dy dx equals, well, obviously everything over here cancels off. So when you multiply these together, we just get 1, okay? Plus, over here we just have the natural log of x plus 1. All right, now I'm just looking for dy dx, so notice I have to multiply both sides by y. Okay, so dy dx equals y times 1 plus natural log of x plus 1. Now, lucky for us, we can get rid of this y by going right back up and substituting from the original function. So y is equal to x plus 1 to the power of x plus 1, so we can just substitute that in there, okay? And so we get x plus 1 to the power of x plus 1 times 1 plus the natural log of x plus 1. Okay, certainly that is one form of the answer. And you could certainly leave it in that form. I'm looking at it and I'm thinking the only other thing you could possibly do is just distribute this guy. So if you wanted to do that, okay, we could write our answer as x plus 1 to the x plus 1 power plus x plus 1 to the x plus 1 power times the natural log of x plus 1. So we could go this route if we wanted to. That's perfectly fine. I do not see how we can mess around with it much more to make it any easier to look at. Because certainly I do not want to take this whole thing and move it back in exponent form, because that would be about as ugly as it gets. So I'd probably leave that go. And that's about it. Those are the two forms that I would accept. All right, last one for today. Same type of situation. I think that we did a problem like this where rather than sine, we were using cosine. I think we did that one in class. Okay, so we'll try this one. So again, this guy is very similar to this guy in that notice that your base basically it can change because it has an x in it. So depending on what x is, sine of x, okay, can change. But remember our general rule, okay, for taking the derivative of an exponential involves an exponential where the base is a constant. So just like the one we just got done with, we have to pull this base and that exponent away from each other, okay? These two have to be pulled away from each other, okay, because they both contain the variable x. Okay, so going back to logarithmic differentiation, that's what we're going to have to use. So let's get this function in a form that I can use. So we take the natural log of both sides. So I get the natural log of y equals the natural log of sine of x to the sine of x power. Okay, and once again, okay, I can pull this exponent away by moving it out front as a coefficient using one of our properties, okay, of logarithms. So I get the natural log of y equals sine of x times natural log of the sine of x. So now notice what we've done. We have pulled the base and the exponent away from each other. So now I can differentiate. Okay, so just take the derivative from left to right. So the derivative of the natural log of y would be 1 over y times the derivative of y, which is dy dx. On the right-hand side, you've got a product. Okay, you've got this function sine of x, and then you have this function, the natural log of the sine of x. So we got to use the product rule. So we take the first times the derivative of the second. So that would be sine of x times the derivative of the natural log of sine of x would be 1 over sine of x times the derivative of the sine of x, which is cosine of x, plus, okay, now we take the second times the derivative of the first, so we have the natural log of the sine of x times the derivative of the first, and the derivative of the sine of x is cosine of x. Okay, so now we got to clean things up, and then obviously eventually I have to multiply both sides by y. So let's see here. Well, sine of x times 1 over sine of x, they just cancel each other off, okay, and so we have cosine of x. And then I'd probably write this as cosine of x, probably put that out front. So cosine of x times the natural log of the sine of x. That's an x, not a y. Okay, and so then now I just multiply both sides by y. So my dy dx equals y times cosine of x plus cosine of x times the natural log of the sine of x. Okay, and then obviously I know what y is. Okay, so I could come back up here and substitute sine of x to the sine of x power in for y. Okay, so let's see, we get sine of x to the sine of x power times cosine of x plus cosine of x times natural log of the sine of x. Okay, and certainly I would say that is one form of the answer, and that would be completely acceptable. I'm trying to think of some way where we could make it maybe a little bit simpler looking. And the only thing to me, I would factor out a cosine of both of these terms inside and maybe put that out front. So another form that might be okay would be, let's see, cosine of x times sine of x to the sine of x power times the quantity of, and if I factor out cosine from both of these, I get 1 plus natural log of the sine of x. And, you know, maybe it looks a little bit simpler. Either one's fine. Okay, so this will be the first video of this week. I will post this as soon as I can, and stay in touch. There'll be some more videos coming this week, and if you need any help on anything, either leave me a message on Google Classroom or just email me. You guys stay safe.